finish it today, and then homework session tomorrow, right? Okay, so far when we've been looking at, as a natural approach to the two-dimensional wave equation, we've been looking at membranes, motion of membranes. And so far we've been looking at normal modes, right? Well, and we've done this before in other systems. The next natural thing to do is have a drive on there. So the basic idea here, whether it's membranes or whatever system you're dealing with, is that when we have an undriven, usually we take it to be undamped system, we can explore it by looking at the normal modes. Usually a more physically relevant problem is what happens when you have a drive. So the difference here is that this omega here, we're going to imagine a sound wave coming in, hitting a membrane. This omega here is the drive frequency, and that's tunable. That's completely up to us, right? Before we were solving for the different omegas, the different normal modes, which have their own frequencies. So just make sure, we've been through this before, I'm just reminding you here. There's a shift of emphasis now when we drive the system. This omega is a continuous variable that we have under our control. We're not solving for omega for the normal modes anymore. The connection between the two is that you're going to get resonances where the normal modes are. And that we will see those in our analysis here. So here's the situation. We have a membrane. We'll assume, I didn't write it, I should have written it here. It's fixed on the rim. We're going to take the fixed boundary condition. This is the standard case for a microphone, a condenser or capacitive type microphone. Circular membrane. And a sound wave is coming in here. Now, I'm just going to mention this. We're going to talk a lot more about it next quarter and in the transducers course. But the typical situation here is that the wavelength of the sound is much bigger than the radius of the membrane. So what that means is, in other words, if this is a crest, the next crest is way up here, okay? So what does that mean when the sound wave passes over the membrane here? What's the difference? You can see when this wavefront passes over here, the pressure is not going to be the same here as it is here, right? You can see that, right? Because let's say this is a max. Right now, this is being hit with the maximum pressure. Assume this is a crest. Right now, this part of the microphone, this part of the membrane is being hit with a high pressure. It takes some time later to hit over there. However, what is that difference if the wavelength is large? If the wavelength is large, there's going to be hardly any difference there. So this is often but not always the case. So when it is, if I got a microphone here, I'm not going to worry. I don't have to direct it to where the sound's coming from. As long as the wavelength is large, it'll pick it up even back here, okay? It'll pick it up fine. Now microphones are corrected for this angle right here. If you want, if the wavelength is not sufficiently long for you and you want to correct for it, there are corrections. You can see these in specifications of the microphone. Okay, so what's our wave equation look like now? Well, you got to go back to basics. Remember one of the first things we did in this chapter was we looked at a little patch of the, imagine we're looking at a little patch of the microphone here, and we look at the forces on there. This is the force due to the curvature of the membrane. When the membrane is curved like this, there's going to be a restoring force wanting to bring it back to equilibrium. So that involves the Laplacian. Remember this is the force per unit length. So we have that force. Now we have an additional force. And because of the long wavelength assumption, or if this bothers you, this directionality here, for this course right now, for the purposes of doing this, imagine that the sound is coming in normally, okay? So at any point in time, the pressure is constant here, it's uniform. Every element sees the same pressure at the same time, right? So just imagine it's coming in normal. So that's going to be, this is going to be the force on the patch is the pressure, which is oscillating, times the area. The pressure is the force per unit area. We multiply by the area to get the force. We get this oscillating force. By Newton's second law, the force is the mass times the acceleration. The acceleration of the mass of the patch is just the mass per unit area times the area. And the acceleration is the second derivative with respect to time on y, on the displacement y. So we cancel the differentials, and this is our wave equation. And this is not surprising at all, is it? Do you see what? This is the standard two-dimensional driven wave equation. We have this non-homogeneous term here. We have the y's over here. This is the drive. You know, the one-dimensional case of this we saw way back in oscillators. So this is very standard case of a driven wave equation. So we're going to look at steady state motion. Now you notice we don't have any damping in our model here, but we assume a slight amount of damping, so slight that we don't have to incorporate it into the wave equation. But we imagine a slight amount of damping so that the system will reach a steady state. It'll be, the membrane will be oscillating at the same frequency of the drive after some time. Typically it's very short. Because you remember there are transients here. The transients are the solutions to the homogeneous wave equation. Remember that? That's why we did all this, all that oscillator stuff. This is, we're seeing it here. And that was a simpler setting. That's why it's done. So focusing on the steady state solution, it's going to be going at the frequency of the drive. So we just substitute, and it's going to be a standing wave. So we substitute the usual, you know, as of yet unknown function of space here, of R. It's going to be azimuthally symmetric. But we don't, let's not, imagine R and theta, function of R and theta, and then the time dependence. When we substitute that into the equation, we cancel the e to the I omega t. The time derivative brings down a minus omega squared, the two time derivatives, and we get this. And as always, we actually get omega squared divided by c squared, but we use this dispersion relationship, so we have k. So you've seen this all, I'm just reminding you, you've seen this before. So it's very similar to a driven, similar to way back in chapter 1, a driven oscillator. Now there will be a homogeneous solution. That's when you have no drive. Okay, that will contain, because it's a second order differential equation, that'll contain two unspecified constants, right? The particular solution is the solution that satisfies with the drive here, and that's going to be unique. It's going to be a unique solution there. Then the total solution is the sum of the particular and the homogeneous. We need the homogeneous solution because we have to enforce this boundary condition. So you'll see that in a moment. The particular solution here is particularly easy. This is just a constant, right? This is a constant. So the particular solution, the particular psi is just going to be some constant. The Laplacian acting on the constant will be 0. So I can see what the particular solution is going to be here. It's going to be minus p over k squared tau. Here, I wrote it here. You can see that when you take this and substitute in the equation, again, you get no contribution here. Multiplying by k squared removes that, and we get the particular solution. It's easy. It's really easy. So what about the homogeneous solution? So let me remind you what that is. I know it looks complicated, but it's not really. I've separated out the m equals 0 solution. So we know that the solutions here for circular membrane to the wave equation are Bessel functions. So here's the m equals 0. This is the azimuthally symmetric solution. Doesn't depend upon theta. The higher order Bessel functions here have successively more nodal diameters. The m equals 1 here is going to have one nodal diameter somewhere. We don't know where, okay, and it's not going to matter here, but in general we don't know where. That's why we have this gamma. The gamma is there to adjust it. So this will be, it could look like this. So here's the m equals 1. I'm just reminding you of all this. It has, this is a nodal diameter, and these two are motions of these two pieces of sections of the membrane are out of phase. And this nodal diameter can lie anywhere. And again, that's the reason for the gamma. The mode can have some amplitude. That's the reason for the B there. And then radially, there is a J1 Bessel function for the radial in the radial direction. And then we, in general, for the general homogeneous solution, we have to sum this up to infinity for all these Bessel functions. And we'll have more and more, you know, when we go to m is equal to 2, we'll now have 2 nodal diameters. They'll be perpendicular to each other. And we don't know the orientation. That would be, we don't know that, etc. Now, why don't all these matter? Well, if you imagine you have this microphone here, and again, go ahead and just take the wave coming in normally, okay, just for simplicity. Can you excite, let's go to the m equals 1. Can you excite this mode, wherever it may be here? I've got sound coming in here, right? Uniform sound. At each point in time, it's a uniform pressure, and the pressure is oscillating. Can I drive this mode? No, it's got the wrong symmetry. It's like a string. It's like a string here. And if we look at the second mode of a string, if I'm exerting a force, a uniform force, all along the string here that's oscillating in time, right? I can excite, if a half wavelength I can excite, it's going to get excited. This is not going to get excited. It's got the wrong symmetry. We could be, for example, we could be putting energy into this half wavelength, but because of the anti-symmetry, we're going to be taking energy out of the other one, so we can't feed any net energy in. So that's going to hold for all of these. You just keep adding more nodal diameters. You're going to have this problem. So these are just, we don't need these due to the asymmetry. So this is actually quite simple here. The homogeneous solution is just going to be the J0, the azimuthally symmetric solution. We don't know the amplitude, okay? That's going to depend upon the amplitude of the drive. So we just leave that. Here's our particular solution. Oh, I'm sorry. Okay, I'm thinking of this. Let me back up here. We've got our, there's slightly different ways you can do this. And this, let me just follow the notes here. Here's our homogeneous solution. Here's our particular solution. Now we already have the information on the drive amplitude is in here. Now we haven't met the boundary condition yet. So the way I'm doing it here, the next step would be to enforce the boundary condition. At r is equal to a, this has to be 0. We're assuming that the membrane is tied down, is fixed at the rim, r equals a. So if we set r is equal to a and demand this be equal to 0, that's going to demand it being equal to 0. That's going to give us this a here. And here's what we have. Here's a nice way to do it dimensionlessly. We have this dimensionless ratio here. Okay, so that's the response of the membrane. It's azimuthally symmetric. There's no angular dependence. That's it. It's actually pretty easy to get here. It has a lot of interesting consequences, as you'll see. We'll go through that today in this lecture. So the typical thing that is done here, and you've seen this in the lab and you're going to see it more and more, is we fix the pressure amplitude and slowly sweep the drive frequency, right? We imagine, and this is theoretical, we're imagining slowly sweeping the drive frequency. We always say slowly because we want to emphasize that we want the system to be in its steady state, right? So the slowly is really comes from the lab, comes from a lab where we want to sweep the frequency, the drive frequency, sufficiently slowly such that it's always in a steady state. And you know, many of you have seen this, right? If you don't sweep it slowly enough, you can see the transients, right? Okay. And that comes up all the time in acoustics. That's why we emphasize it. So the math tells us here. Now remember, I know this. You want to remember here, omega is equal to ck, right? And omega is we have complete control over omega. It's the drive frequency, right? So we're not doing the normal modes here. So you want to think of this is proportional to frequency. As we sweep the frequency, we start at a low value. What's going to eventually happen? J0, remember what J0 looks like? In fact, I think I have a sketch here. Let's go ahead so we can look at the sketch. Here's J0, and I've extended here in the red. J0 starts off at 1, and it's roughly sinusoidal-like, and it damps out, right? And if you get away from the origin here, sufficiently away from the origin, it is a damped sinusoid, okay, as we discussed. But that approximation only holds. You have to be away from this region right here. So J0 looks like this as I'm sweeping frequency, which means I'm sweeping the K value here, okay, because omega is equal to ck. Eventually what's going to happen? We hit this 0, the first 0 of J1. And these are in the back of the book, right, in appendix. So what's going to happen? What's going to happen when this goes to 0? This is not going to be 0. R is less than, unless we're on the rim, but just stay away from the rim, we're going to get infinity, right? So we hit a mode. We hit a standing wave mode or normal mode. And in our model, because we have no dissipation, it's going to blow up. We get infinite response. Now, when I first looked at this section years ago, I decided it was best not to deal with dissipation because it makes it more complicated. And I think it's good just to see through the basic physics here. So that's why I didn't include dissipation here. But the textbook does. KFCS has dissipation. I think they probably use a complex K, right? But I just thought that it sort of clouded the issue. So that's why I'm presenting this with no damping. But realistically, there's going to be some damping, and that will prevent. We're not going to get infinite response, okay? All right. Now, the next thing here is what's relevant for the response of the membrane. The membrane responds to the sound wave. And what's important in its response is just the average displacement. And I can jump ahead here a little bit and show you why. Wrong button. So here's a standard capacitive type, or an older word people also use is condenser microphone. You see the capacitor here, there's two conductors. The membrane here is metallized. It has some, it's typically how it's done. They've put a very thin layer of metal on there. Often you can see through the membrane, but that doesn't mean there's not a metal coating. There's got to be, okay? And then, so that's one plate of the capacitor. of the parallel plate capacitor. Here's another plate. This plate is fixed, okay? The membrane is stretched. There's an axis of symmetry here. This all has symmetry about this axis here, right? So there's this ring. The ring looks like this. The membrane has been stretched, attached to the ring and stretched. That's the membrane here, and it's metallized. Here's the fixed conducting, the other side of the capacitor, the other plate. It's a fixed conductor. There's a gap here, right? And for this to work, of course, we have to have it charged up. So you charge this up, and when a sound wave comes here, it's going to move the membrane. For a fixed charge, the voltage will change here. The voltage is, for a parallel plate capacitor, the voltage is the electric field times the distance. So this is the distance. Here are the two plates. And this is the electric field between the plates, which looks something like this. And it's approximately uniform. This is the electric field here. And some of you, we don't want to get into this right now. We will later on. Actually, probably not until the transducers course. But some of you may remember this from, it's elementary electromagnetism. Some of you may not remember it. You've all had it sometime in your past, right? I'm going to keep reminding you of that. And you'll see why when we do the transducers course. Okay, so the point here is that for fixed charge here, call it Q naught, and here's minus Q, equal and opposite charge on this capacitor here. The sound wave's going to cause this, modulate this distance is going to change. The electric field stays the same because it just depends upon the charge. But the voltage is going to change because this distance is changing. And that's how it works. That's the basic idea of a capacitive microphone. Now there's a problem here. How do we keep the charge constant? Well, the cheap way is to not have this construction, but use an electret material. This is a solid material that is permanently polarized. It has permanent charge here. It's a dielectric, it's a piezoelectric type material. We'll talk a lot more about that in the transducers course. But here, due to the alignment of the dipoles, there's a slab right here. It's permanently, the charge is permanently on there. You can't remove it. That probably seems strange to you, but we'll explain it. It's actually simple. We'll explain it in the transducers course. Those microphones are not very high quality though. These are much higher quality. So we have to find a way of keeping the charge on there, because otherwise, what's the charge going to do? Imagine there's a water molecule that's coming around here. You know, some humidity, right? The humidity is not zero. Water molecule comes here. It can get attracted. I don't want to get into the physics of this, even though it's really simple. We can't do it right here. But a water molecule can come and stick here, and then what can happen? It can pick up. It can give up an electron to cancel this plus, and then it becomes positive, and it gets repelled away. That's almost always how things discharge. There's other ways that when charge builds up that it can discharge, but the most common way is due to humidity. I don't know if you knew this. So what happens in Antarctica? What's the humidity? Really low, right? So objects stay charged. So you might think, oh, that's nice, all we have to do is charge it up, we don't have to worry about it. Yeah, but you got other problems. You can walk across the floor of some lab in Antarctica and touch some equipment, and what happens? You can zap it, okay? You pick up, just by friction, people pick up a net charge. So people in Antarctica, I read this once a long time ago, I've never forgotten it, they have to always stay grounded, because otherwise they'll just by friction. You know how you can charge things by friction, right? You've all probably experienced that. They can destroy equipment. Right? So anyway, here we have to keep this at a constant charge. So what it's done is we have a DC voltage source here. It's typically 100 volts. All right, for this kind of for capacitive microphone, it's not real high. It doesn't have to be real high. And we charge this up through a resistor. Okay, so, and assume we don't have the resistor first. Here's some voltage source. All right, so I've charged it up. Great. What happens when a sound wave comes? It pushes, it's going to push this, when the positive pressure is going to push the membrane down and up and down. What happens when the membrane goes down? Well, the job of this is to maintain a constant potential difference here. So what's the problem there? No. No, if they touch, you're in a highly nonlinear regime, and this can happen. I've seen it in microphones. It's kind of interesting. The microphone then rings down at its own at the natural frequency of usually the fundamental mode. You can actually see that on an oscilloscope. But don't worry about that. Remember, we want to have a transducer here. We want to convert the sound to a voltage that's easily measured. If we keep the voltage across there, what are we going to pick up? Nothing. We're just going to see that voltage. We're not going to see the sound wave. So the trick is, and it's pretty simple, you want to put a resistor here. This will then have an RC time constant. Does that ring a bell? You make sure the time constant here is sufficiently long compared to the period of the acoustic wave. So when this wave comes here, it's going to modulate the distance between the plates like this. We have this resistor big enough so there's not enough time to keep the voltage across here constant. That's what this thing wants to do. So its purpose is just to leak charge on there. As charge goes off, usually by humidity, as I described, this will keep it charged up. It'll keep the equilibrium without the sound. It'll keep the equilibrium charge here constant. And when the sound waves comes, because the time constant here is long, it won't have time to change the charge, to keep the voltage constant. So that's the standard trick. Now, getting back to our calculation here. What's important here, when the voltage changes, the voltage picks up on of course, the whole geometry here. And it's reasonable, and it can be shown, that all that's important is the average. Our membrane is actually going like this. It's not going like this. This is assumed in a lot of transduction problems. We'll assume it too. We can assume that the membrane is doing this for simplicity, but it's actually not, right? It's doing this. So you can see here that what's going to be important is there's an average distance here. And that's what's going to be important when it changes. It's how this changes, this average distance here. So that's why we have this, and we've calculated this before. That's why we deal with the average displacement over the surface. That's going to be proportional to the voltage. Okay. So, I skipped over this. Now let's go back to here. Let's calculate the average displacement, because that's what's going to be proportional to the voltage, what we're picking up here. We have our y. We would just multiply this by e to the I omega t, and then we need to multiply this by, we went through this yesterday. We need to find the average. We multiply by a little amount of area, and because of this axial symmetry here, we're just going to take a little strip here, the 2 pi r dr, because all the y's the displacement is the same along that, for that analysis. So we take our displacement multiplied by the area, integrate, and then divide by the total area. That's going to give us the average y. So the constants come outside the integral. We did this yesterday. And it's amazing that we can do this integral exactly with a recursion relationship. It involves J2. You can look back. That's what we did yesterday. It involves J2. So that's very nice. Yeah. We don't have to dealing with this numerically or anything. It's just equal to this. Okay, so now we have the average displacement. And next, what we want to do here is consider the response of the microphone. Now, we have a sound wave coming in, right? The typical application here is when the wavelength is large compared to the membrane here. So what that means is, and we'll push on that, we will exceed that, but let's just, for the moment, let's consider that situation. We summarize that the correct way to do this from a dimensionless point of view. When the wavelength is large compared to a distance, in our case it's the radius or the diameter. We're going to see this again and again next quarter. You know, it's going to be some geometrical parameter. The correct way to state it is Ka is much less than 1. Because K is what? It's 2 pi over the wavelengths. Okay? So, this would be the typical operation. And now to see what our theory tells us here, here's our theory. This is exact. We can approximate it for Ka much less than 1. What's J0 of a small number here? By now you should start to see this in your head and not hesitate. It's 1, right? Because it's always good to keep this in your head. J0 is the only Bessel function that starts off at being non-zero here. And it has this stamped sinusoid. And it starts off it's normalized to 1. It's just chosen to be 1, okay? So J0 for this low frequency or long wavelength sound compared to the diaphragm radius, the radius of the diaphragm, we're going to be down in this region right here. This is flat. This is approximately constant right down here. Okay. What about J2? We also need J2. Well, I don't know if you remember, but I told you a good thing to keep in your head, and it's easy to remember, is that Jm has a 0 when the argument is 0. Except for J0. And the 0 has an order equal to m. So what I mean by that is, when you see J2 here, as the argument goes to 0, this is going to go to 0. And it goes to 0 like a parabola, because it's got a 2. So it's going to go like, calling this x. So let me write this down. J2 of x is going to approximately be proportional to, let me just write that. It's going to be x squared. In fact, Jm of x is going to go like x to the m. And this is for x small. Okay, when you get close to the origin, it's going to go like this. And this actually works for m is equal to 0, because what's x to the 0? It's just 1. So the fact that the Bessel function of order m has a 0 of order m at the origin, it's easy to remember, and it's useful. So what happens to this then, J2? Well, here's where I have to look it up. I don't remember. But I want to just point out to you that J2 has to come in like this. It's going to come in like a parabola here because it's going like Ka squared, x squared. What's the coefficient? Well, you got to look that up. I never remember that, okay? And it's in the back. It's in our book. It's in our book. And it's a standard, in any mathematical physics, it's just standard information on Bessel functions. These, asymptotic behavior and low argument behavior, standard. Look that up. so we make these approximations. Jz is equal to 1. J2 is equal to this, in this region right here for low frequency. And do you see what's going to happen here? This is really important. What's going to happen to this k squared? Remember, this is proportional to k squared, right? Because it's parabola. It goes away. That's extremely significant. What it means is that in low frequency limit, here's the full expression. Here's our average displacement. The voltage will be proportional to this, right? That's why this is important. How does the voltage depend upon frequency? If I keep the pressure amplitude of the sound wave constant, how does my voltage change if I change the frequency of the wave? You see it here? Do you see any frequencies in here? Any K? No. Okay, everybody in the world calls that, this is so important, it's got a name. It's flat. The microphone is flat for low frequencies. Its response does not depend upon the frequency. If you hold the amplitude constant, in this case it's for acoustics, this is general for all transduction, okay? Where frequency is involved. So if we have a sound wave coming in and we change the amplitude but keep the frequency constant, if we change the frequency but keep the amplitude constant, okay? So we're going to keep the amplitude constant, P is a constant. We change the frequency, we get the same voltage. That's very desirable. Sometimes you don't have that luxury, and then you pay a big price. But it should be obvious to you that that's desirable. We have a sound wave, we keep the amplitude. We want the voltage to be proportional to the amplitude of the sound wave. That's the basic idea here of transduction. In this case, of transducing sound. We want the voltage that we pick up to be proportional to the amplitude. If we change the frequency but keep the amplitude, if we change the frequency but keep the amplitude constant, we want the voltage to stay the same. And it does. But only in the low frequency limit. Okay? So you need to be aware of that. I'm going to drill this into you starting next quarter, and then we hit it big time in transducers course.
Does that relationship hold for like non-cylindrical geometries? I mean, right now we've just proven that with like Bessel function, but if it was a square transducer, would you get the same cancellations? Or?
Yeah, I think so. Yeah. In fact, we've seen this all before. The reason I feel strongly about that is, I hate to say it, but think chapter 1, the harmonic oscillator. What was the response of the harmonic oscillator when you're well below resonance? Oh, by low frequency here, we mean below resonance, right? What's setting the scale here? Remember here? This is resonance. How does the oscillator respond? We called it the stiffness controlled regime. Right? We also called it the quasi-static regime. So when I'm driving an oscillator at low frequency with a constant force, I have a force amplitude. I'm driving it at some frequency, relatively low frequency, and I'm keeping the force amplitude of the drive constant. As I change the frequency, what happens? Stays the same. Right, remember this? Spent a lot of time. Here's what it looks like. So this is just for a standard oscillator. This is a driven oscillator in the steady state. And we're keeping the force amplitude constant. We're changing the frequency. It's a very common case, as you now know in the laboratory. We're sweeping frequency slowly, so it's in the steady state, and we're keeping the drive amplitude, the force constant here. And here, and I can make this, let's make this more dramatic. This is not actually realistic, the scale here. The more typical case is this, okay? This is more typical. So we have this nice, flat regime here, which is very desirable for transduction. Very desirable here. Because in our case, this amplitude, this translates to voltage when you deal with transduction. Okay, so that's just the introduction. We'll talk a little bit more about it next quarter, and then we just get immersed in it in the transducers course. But it's good to start getting these ideas in your head now. It helps. Any other questions so far? We just got one more page here. Let me see if I'm missing something. Right, okay. So, here's the idea. And again, the scale is really not right here. Typical scale, the typical bandwidth here, you know, is the quality. This is really a low. Let's see, what am I trying to say here? Typical case is, you know, the resonance is much more local to this out here. There's a much bigger, relatively big flat regime here. But this is what our average Y is, which is proportional to the voltage. That's what we measure. And here we have this flat regime here. And again, this conveys it better here. I went kind of asymmetric on the peak there, didn't I? So this meant to do this. Got a little carried away, so it looks something like this. Oh, I can do this all day. All right, so this is the typical case where the quality factor is not of order unity. And you know that's going to be the bandwidth here. The quality factor is basically what the width is here compared to this. So as long as you're not in very low quality factor, there's this nice flat regime here. And this is where you want to operate the transducer. But that shouldn't stop you, especially when you're learning about transducers. That shouldn't stop you. You shouldn't restrict yourself to this. Because let me tell you what happens in research. You're going to end up over here. Okay, it almost always happens when unless you've got some fixed, simple task you want to do, hook up a microphone to measure something, and it's not a research situation, then you can get by with operating here. But I've seen this so many times where you've got to know the limitations of your transducer. Maybe that's the best way to say it. Because in research, you're almost certainly going to be probing those limitations. And if you don't understand, you can get yourself in a lot of trouble. Okay, so let's explore this. Let's see what happens here. So this is the first mode. That's when we hit resonance. Here's the normal operating regime down here. We're going to hit resonance. So what standard design, this should be a design, not ideal. The designed, how did I say this? Designed, typically in microphones, what they do, it's better to replace this ideal, I don't think that's appropriate here, with design. They adjust the damping in the microphone. Okay, so otherwise you'd get this big peak right here. They bring this down from where it would be just due to the natural damping. They add damping to bring it down to extend the flat regime. Now it's not exactly flat, as you can see here. And what they do, and this is very common, it's just every microphone, unless it's really cheap, they do this. This is one of the things you're paying for in a microphone, a quality microphone. There's a little rise here, and so it's not exactly flat here. But if you're concerned about that, if you're doing something very precisely, you'll have in the spec sheet, you'll know what this is. They'll tell you, or you'll actually see the graph here, calibrated here, so you can correct for that little rise. They put a little rise in here, and they do that because if they could just have it go like this, but they're trying to extend that flat region as far as they can, okay? Because ultimately people push. It's just human nature to push on things, to explore limitations of everything. This is the way. That's how we evolved, or part of our evolution. So they put this little rise in here to try to extend this out here. And then if you do get out here, then you want to be careful. You're losing what we call sensitivity. That's a very specific term in transduction. We'll introduce it next quarter. Here you're getting, you're seeing less voltage, okay? But you can, this is quantified. You'll be able to account for that, right? But what eventually happens? Look at the sketch there. Eventually, this hits 0. And the reason, mathematically, it's hitting 0 because J2 has a 0 at 0, of course, because it's all Bessel functions of order 1 and higher have a 0 at the origin. But you know it's going to be a damped sinusoid, so here it turns out to be approximately 5.136. It's 0. So what is our exact, this is our approximate theory. We got to chuck that right now, right? This is the theory for down here. So we got to go back to the accurate theory. Here it is. No, here it is. So at 5.136, or what is it, whatever it is, what's going to happen here? We get no average displacement. So how does that come about? Well, as we go to higher frequency here, the membrane's going like this. Eventually, there's going to be a node coming in from the boundary here. As you slowly increase the frequency, there'll be a nodal circle that comes in from the rim as you slowly increase the frequency. And here it is at some later time. And this Ka value here, which will correspond to a certain frequency, is where this area, you know, the average area is 0. So this is coming out, this is going in, and they exactly cancel. So the voltage is going to be 0. We're going to get 0 voltage here. This would be a great demo. And most microphones, audio microphones, they start to roll off around 20 kilohertz. That's typical. That's the limit of hearing for young people, okay, very young people. So it'll roll off at 20 kilohertz, but we can drive this, it would be ultrasonic. The demo, you wouldn't be able to hear the sound because we'd be above the limit of human hearing. And, but you can look at the voltage on the oscilloscope, and we should, as you slowly increase the frequency, it should be a point where it goes to 0. And then if you increase the frequency more, it picks up again. And one nice thing about driving it ultrasonically is we can drive it really hard because you can't hear it. Because there may be some signal to noise issues. I don't know, I've never tried this. I've never done this. I forgot about it until I saw this. But it would be an interesting demo to do. Is there a question? Okay. One final thing here. So this makes sense. The average in our microphone here, our capacitive microphone, the average displacement for this frequency right here is 0. You know it's going to happen. There's going to be a frequency for which that happens. And it's dictated by the 0 of J2, this number right here. Is the membrane moving? This is just an interesting question. KFCS say no. Well, they didn't actually say no. You can look at this. They say it's very small or something, or it's small or something like that. And it's reasonable. Remember when I was, oh, here, it's still here. It's reasonable because it appears like what we might be having here is something similar to this kind of situation, where we can't drive this mode. This particular value of Ka here, it looks like we've got the wrong, you know, we're not going to be able to put energy in there. But I think KFCS made a mistake. I think it's wrong. And let me explain to you why. The math, so it's reasonable that the membrane wouldn't be moving. And I hadn't seen this, you know, for 4 years. And when I saw this, I decided I'd made a mistake. But I kept thinking about it. Look, we've got the theory here. We've got the math. Look at this. Here's our displacement function, right? Can this be 0 for all r at any value of Ka? There's no way you can zero this out for all r going from 0 to a, right? There's no way this can be what mathematicians call identically 0. It means 0 for the r in our membrane here, for all r values in the membrane. So I don't think it's true. And maybe what's happening here is, I haven't analyzed it, but maybe it is a small displacement. Maybe that's why Ka KFC, you can read it, it's in there. They don't say that the displacement's 0. They say it's small or very small. So I don't know. But it can't be, we don't have this kind of situation. We have a different geometry. This is circular geometry. Things can be different. So I don't think it's going to be 0. I think there's going to be some displacement there. Okay, are there any questions or comments? Okay, does anybody have any questions? We're getting near the end of the quarter. Anybody have any questions? So I sent out that about the problem sets, right? So you can turn in old ones. It's really good to do the problem sets in a timely fashion. But you know, I know people get really busy, especially around here, and also for the DL students. So you can turn, but I have an absolute deadline on the homework, okay? And I'm starting to put it on quizzes too, right? So your quizzes are graded. So I'll try to do the DLs tonight. And so you can see where you stand, right? And the DL students see this too, except the names are removed and there's a code. Did I tell you guys about that? I can't remember if I told you about that. Yeah. So, and the reason we do this, and I'm not the only one, I just found out, Professor Kopolka does it for this reason too, is we don't like to admit this, don't tell anybody, that we make mistakes. It's typically with problem sets, you won't get credit for something that you actually did, so you want to make sure you check this. And I thought I was the only one, but then I talked to her about it, and she said, oh yeah, that's why I show my students the grades too. She uses the grade book in Sakai. It has a grade book. I just don't like it. I like to use Apple's numbers, so that's what that is. All right, so make sure you check, and if you have any questions, you always come by and talk to me, right? Okay.